Hey, Physics 30s. So we are going to finish off that first part of our lesson here. Or the first lesson, the second part of the first lesson. So we're going to talk more about Maxwell's predictions. So you are going to have to know those 5 predictions and the 5 properties of transverse waves. I could ask questions about them. Most of the time I don't ask you specifically what are the 5 properties of the transverse waves. So these down here, I don't ask specifically about them. I might ask questions more focused on them. I might say a wave reflects at this specific angle, talk about the law of refraction, Snell's law and stuff. But the 5 theories up here, I could ask this. I can ask them maybe on a quiz, one of our quizzes here. Most of the time when I ask these kind of questions on a quiz, I don't just say list off the 5. I might just say, okay, which of the following 4 is one of Maxwell's predictions? Or which of the following is not one of Maxwell's predictions, right? So I might just say something like that. Yeah, it'll make it a little bit easier. I'm not just going to say, wrote out, just use your memorization and find all 5 of these predictions. Just find the one that's wrong. So hopefully you can kind of reach back in your memory and find that. But there are things you're going to have to memorize, such as, since Maxwell predicted that light is the type of EMR due to the speed of the waves, EMR covers this huge broad spectrum, which visible light, now I don't like this, I've got to change this, but visible light is a very small part that is detectable by the retinas of the human, in humans. I say humans because different animals can detect different types of spectrum. Some animals can detect infrared, some animals detect ultraviolet. We can take pictures of ultraviolet using special filters on our cameras. The same thing with infrared as well. But humans, very specifically, the visible light spectrum is a very small part of this whole light spectrum, of this whole EMR spectrum. Okay? I'm just going to kind of put some extra pieces in here. So this should say visible light. He predicted that visible light. If I can get this to write properly, it's not right anymore. Oh, seems like my little cursor here. Oh, there we go. A little problem there. This is the visible light. Was the type of EMR due to the speed of wave. So remember what I was saying, if I just say light, that just means all of EMR. If I say visible light, that's just this really small section. So here's this picture. Now, yeah, I'll use both the 2 pictures here. They both kind of represent the same thing. The reason I like this picture here because it kind of gives a good indication what this light, what light looks like here, and a pretty good ordering of how the waves or the spectrum goes here. Same thing on this one too. I do like this one because it has this comparison to everyday objects. Like here's Mount Everest. There's a skyscraper. That's how big they are. Fingernails, atoms, and then the nucleus and stuff. I'm not too worried about the stuff on the bottom here. We'll come back to that. Okay, so what you have to know out of this at this point is either one of 2 things. You either have to know the ordering of the waves based on frequency, or the order of the waves based on wavelengths. But you don't have to know both. But essentially, if you know one, you know the other anyway, because if I know, say, if I know the frequency, I can always find the wavelength, because the wavelength is just going to be the speed divided by the frequency based on the universal wave formula. And if I know the wavelength, I can find the frequency. So based on this formula, you can also see that why on this side over here, if my wavelength is huge, these are gigantic wavelengths. These are measured in, they're measured in micrometers, but the micrometers times 10 to the 10. Micrometers is still pretty gigantic. You'll see in the picture down there, that's like the size of Mount Everest. Why there's such a large microwaves, or here for wavelength wise, but there's such a small frequency. 10 to the 5 is pretty small for EMR. You can see that my frequencies are increasing as I go this way. So I get bigger and bigger frequencies as I go this way. But if I were to go the same way on this side, they get smaller and smaller and smaller because they're inversely proportional to each other. If my wavelength goes up, if this number on the bottom here goes up, then my frequency will go down because I'm dividing by a bigger number, or vice versa. If my wavelength goes down, so my wavelength goes down, my frequency is going to go up. right? So they are inversely proportional to each other. So that's good to know. So if you do know one, you don't have to know the other. I'll always be talking about wavelengths. Now, what you also have to know about wavelengths is the ordering. So radio waves to microwaves to infrared to visible, ultraviolet, X-rays, and gamma rays and cosmic rays, we usually just group them together. So this is gamma rays. Now this little kind of Y looking thing here, that is a gamma. It's a symbol. It's like a, technically like kind of like a Y in Greek letters. It's just a lowercase g. It's kind of, if you want to look at it, kind of looks like a, I don't know how you'd say that, like a ribbon, an upside down ribbon, right? But the tail's a little bit longer, but that's essentially what it is. It kind of looks like a Y in this little picture. We say Y rays, but it's actually gamma rays. So this actually stands for gamma. Okay, so this is a gamma ray here. Okay, X-rays, ultraviolet. You can see on this side they got really small wavelengths, high frequencies. Now, what you need to know is the cutoff points for visible light. Okay? It's just nice to know those. I might ask some questions about this where I might ask you what kind of light is this? Is it visible light? Is it infrared? Is it ultraviolet? You can't really know those unless you kind of know what these cutoff points here. So these cutoff points, the 0.8 and the 0.4, I'm just going to write them down here in the bottom. So on the red side, 0.8 is technically 800 nanometers, and the violet side on the other side is about 400 nanometers. That's just a quick change from micrometers into nano. It's easy to memorize the nano because that's what we're going to do. We're going to be changing our wavelengths into nanometers all the time, so I can kind of see what kind of wave it is. So that's good to know. And also just to know that the ordering of the visible light itself. On the 800 side, that's a red, right? On the 400 side, that's the violet. And then what are all the orders in between? It's just more or less, you just have to kind of really know red and violet. Knowing the in-between is great. You got your Roy, G, Biv. Well, indigo is not really a color, but it's just kind of there to make this kind of a word. So Roy, G, Biv. It's backwards. Obviously, I'm just reading backwards here. So it's a Roy G Biv. Up here, you can kind of see it's in the proper order. This is Roy. Oh, there we go. Roy G Biv. All right. Oop. Roy G Biv. I missed the B in there. There you go. Roy G Biv. Okay, so just to recap. Okay, so you have to know. If I go back up here, you have to know generally what are Maxwell's 5 predictions. I'm not just going to ask you straight out to write all 5 predictions. You have to generally know the properties of a transverse wave. Okay, reflect, refract, diffract, interfere, polarize. And you have to know the ordering of the magnetic or the EMR spectrum from radio waves all the way down to gamma rays. Okay, so radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma. Okay, and you have to kind of know these cutoff points on the outsides here of what visible light is. They are kind of wishy-washy. Like 800 is not set in stone. 400 is definitely not set in stone, but those are approximately the cutoff points of red and violet light. Okay. This slide here is just for the fun of it. You can just look at this and say, okay, this is kind of cool. Radio waves over here, they're pretty large. Even microwaves, they're pretty large in comparison to other things. We always think about why there are little holes on a microwave door. Like if you ever look at the screen of a microwave door, there's a bunch of these little holes. Those holes are specifically designed to let visible light, which is smaller than microwaves, to pass through. Because usually light cannot travel through something that is significant. I think it's about half the size or whatever of what it is. So here's my microwave. Here's the hole. It's not going to fit through it. But visible light should be able to fit nicely through the hole. So that's why the holes are there to stop the microwaves from coming out, but to let the visible light in and out, because the visible light is much smaller. Okay. Yeah, you can see here as you go, visible light is in the dustus range, bacteria. X-rays are in the virus and slash atom range. Gamma rays are down to the nucleus level, like 10 to the negative 15 meters, femtometers, which is nice to know that. Usually that's kind of the scale of what they affect as well. So that's why microwaves kind of affect water a little bit more because they're close to the size of water molecules. It's less close to the size of your fingernail, but the microwave is going to affect the polarization of the water molecules too. All right. So I'm going to stop that one. It's a good one to stop there. That's just a lot of information as well about what you have to know. Now we're going to go into more or less some of the mathy parts in the next part of this lesson here. And we'll talk about Hendrik Hertz as well and what he produced, and we'll have another link for another video there. All right, I'll see you in the next video.